Dr. Dawood is the author. What is an antenna? Obvious question. Historical background. Antennas have been around for more than 100 years. Our own Jagdish Chandra Bose did a lot of original work in this direction. He was almost at par with people like Marconi. So there's a lot of history before antennas became practical reality. How do they radiate? What are the typical performance parameters? What are the different kinds of constructions? Antenna arrays, smart antennas, and beamforming is something we'll talk about later. Okay. This is the definition of an antenna. It's a usually metallic device. It may be non-metallic also in special cases, but generally it's a metallic device, a rod or a wire, which either radiates or receives a radiated signal. IEEE has a more concise definition. You can see it here. Now, a wireless system conceptually can be drawn this way: transmitter and receiver. One antenna on the transmitting side, one on the receiving side. Input to the transmitter will be data or your voice. Output will be modulated data or voice up converted to a very high frequency of the order of gigahertz typically. That signal containing the info you want to transmit will go through the antenna, will be radiated out to air or some other medium. On the receive side, another antenna may not be identical to the transmit antenna, it may be different, but it would receive the signal and feed it back to the receiver, which will do the opposite of what the transmitter did. So in theory, whatever you sent should be coming out from the other side of the receiver. In practice, it is not possible to do it 100% correct. But antennas play a very important role in improving the overall performance of a wireless communication system. Okay. The symbol for antennas, as you have seen, is a triangle with a straight line. But depending on the nature of antenna, some people will draw a different signal, different symbol also. (1842) is the beginning. Long time ago. Maxwell, 1864, came up with theories. Edison did a lot of work. Hertz did a lot of work. Marconi did a lot of work. And they have forgotten to mention J.C. Bose here, who was contemporary to Marconi for sure. Bose was an experimentalist. He was not a theoretician, but he understood theory well enough. Okay. So he should be mentioned here, in my own opinion. Right. Okay, you forget this. We'll be confused. What is radiation? Similes are there. If you drop a stone in a water pond, you see disturbance radiating out in circles. And if you observe the disturbance at a very large distance, then those circles will almost become planes. This is the so-called plane wave propagation mechanism. Now, in EM waves also, something similar happens. The time-varying charges or time-varying currents essentially create disturbance that travels. Initially in a spheres, but as you go away and away from the disturbance, those spheres almost start looking like planes. So it's very difficult to explain radiation physically all the time. Mathematics has to be brought in. Time harmonic signals, as you well know, are cosine signals or sine signals, or in a phasor form, e to the power j omega t type of time dependence. So this is essentially telling you what you already know. Signal repeats itself after a time, which is known as time period. These are the formulas. In time domain, we write a sine omega t plus phi. In phasor domain, what we do is we write sine of 2 pi ft plus phi as real part of e to the power j 2 pi ft multiplied by e to the power j phi. And then we remove real. It is there, but we remove it out. And the rest of it is known as the phasor representation of the time domain signal. Phasors help in simplifying the mathematics. Differential equations become algebraic equations. Okay, this is too confusing right now. We'll someday come back to this. Now, antenna does not normally radiate uniformly in all directions. Depending on which direction you are looking at, it may have more power coming or less power coming. So that effect is described by a performance parameter called radiation pattern. It's a 3D plot. Okay, power pattern means you are plotting power. Radiation pattern means you are plotting the magnitude of E field coming out. They are related to each other. Okay. If your antenna is very small, it will almost uniformly radiate in all directions. Then it is known as omnidirectional antenna or isotropic antenna. But that's a hypothetical case. Most practical antennas are not isotropic. That's for sure. Okay, let's not worry about it right now. I'm going to finish this presentation quickly. Gain means in a certain direction, how much higher power you are getting compared to the average power. Not exactly average power, but compared to something average. We'll be going through all the definitions in detail anyway. The input impedance of the antenna is also a very important item to match the antenna to the rest of the system so that maximum transfer of power can occur. We'll come to effective aperture, etc. later. Bandwidth is very important. Does the antenna operate over a single frequency? Does it operate over a narrow band? Does it operate over a wide band? Depending on that, the design will be totally different. The polarization concept you already know from electromagnetic theory course. The locus traced by the tip of the E vector is known as polarization. The best performance occurs when transmit antenna and receive antenna have the same polarization. We try our best to achieve that. Some real life antennas. One piece of wire you see on the left hand side, a very thin piece of conducting wire broken in the middle where a coaxial line feeds it through some impedance matching network. This is a dipole antenna on the left hand side on the top. You can make that wire a circle, then it becomes a circular loop antenna, which has its own properties. A lot of these antennas were derived using common sense and intuition rather than mathematics. Later, we applied mathematics to understand what was going on. The third one from the left on the top is called folded dipole. For low frequencies, the length of the dipole antenna is very large. It is related to the lambda involved. Okay. And low frequencies means lambda will be high. So if the length is too large, it becomes mechanically very difficult. So we fold the length around. And the third candidate you see is the folded dipole. Same length, but folded. That makes it more practical to implement. And fourth one is known as monopole, where half of the dipole antenna is there, but the other half is gone. And instead you have put a perfectly conducting plane, a copper plane. That has its own advantages. And so on. There's a lot more detail they have shown here, but I think, okay, log periodic is a construction of antennas, which is very wideband in nature. I'll be talking about it later anyway in detail. So let's not get too confused. Yeah, this is one thing you will be seeing later in the course. A rectangular waveguide opened up slowly to bigger dimension in both A and B directions. That is called a horn antenna. It is very popular. Okay. I'm sure you saw this in the lab, in microwave lab. We have quite a few of these. This is this is rectangular waveguide with some slots cut on one of the walls. That is another way of implementing antennas. Lens is optical concept brought to microwave frequencies. If time permits, we'll go through lens antenna in detail. Microstrip antenna. Rather than having a microstrip line, you essentially cut off the microstrip line on both ends and you generate a rectangular or non-rectangular radiating aperture on the top of a dielectric material. The bottom is fully grounded. That means full copper on the bottom, of course. We will be going through details of all this later in the course. Don't worry about radiation pattern too much. It's a complicated topic. Array means lot of similar antennas co-located and fed differently with some phase shift between them, and even the magnitude of feeding current may be different. It is a very vast topic by itself, but it essentially gives you flexibility to design antennas with much better performance than what you can get from a single antenna, and so on. Okay, smart antenna, we'll be talking about it later anyway, but it essentially means it changes its performance depending on what is going around it. 5G systems in particular have a lot of intelligence built in around the antennas. Even 4G systems had that. And it is not actually the antenna, it is the signal processing side of what is going as feed signal to the antenna, which is intelligent. Antennas are generally incapable of being intelligent by themselves, but signal processing side is what makes them intelligent. They react to what is around and they change their performance accordingly to give you the best overall performance of the system. So I think this was a reasonably good document. These documents which I am showing you, you don't have to memorize anything. They are more for your reference. Okay. Another gentleman is trying to tell you about antenna fundamentals. A lot of things have been told to you already in the previous ones. What they are saying is, if you take a transmission line and on one end you start opening it up, you get an antenna. As simple as that. This is the definition which I was telling you as well. An antenna is a device that provides a transition between guided electromagnetic waves in wires and electromagnetic waves in free space. Okay. So, yeah, just quickly showing you what I think I have already shown in the previous one. It's a small document, I think. Not much new here. This formula, lambda equal to C divided by F, will be used again and again in the course. I think you know this very well. For 100 megahertz signal, how much is lambda? Use the formula 3 multiplied by 10 to the power 8 divided by 100 multiplied by 10 to the power 6, you get 3 meter. This calculation will be required again and again in this course. For higher frequencies, the antenna size is small. The antenna size, no matter what kind of antenna you're looking at, the antenna size is a function of the operating wavelength. For lower frequencies, antennas are bigger. For higher frequencies, they are smaller. As simple as that. These are some practical antennas. You see a lot of dipoles put together on a single beam to create an array. And this gentleman is there trying to fix the length, etc., and spacing, etc., to get the best performance, I suppose. Okay. This actually is not an array, I think, because they are not feeding each element, but fine. At least you have got several elements coming together to give you overall good performance. Second antenna you see is a parabolic dish antenna. You see it all around you. It creates a very narrowly focused beam of EM wave. which can directly talk to the satellite somewhere up in free space. Okay. Many more antennas given here. I think I'll avoid all this. Okay, so rather than wasting your time, quickly rush through, you'll get it. Oh yeah, one thing important, you have to realize that antenna measurements, that means all the performance parameters that you have designed the antenna for, they need to be measured experimentally. Antennas, although we don't have this facility, the measurements are normally done in a special environment called anechoic chamber. And here you see photographs. Defense labs in Jodhpur have this facility. I have visited them quite a bit. Essentially, what it means is any radiation, spurious radiation coming out from the measuring setup is absorbed by the walls of the room because walls are made of lossy material, cones, lossy cones of special material. So anechoic chambers, at least remember the word, that anechoic chambers are a must for accurate antenna measurements. In our lab, we don't yet have anechoic chambers, but someday, hopefully, we will. Rest is well-known things. Okay, so I think yeah, that's fine. Now I think I'll get back to my own documents. I'll send you these documents so that you can keep them as a reference for future. Antennas, by the way, can be a lifelong career for each one of you, whether you go to academia or whether you go to industry or whether you do both. Good antenna engineers are short in numbers around the world. Yeah. Antenna basic 2, I think, doesn't have anything new, but let me double check this. Yeah, there's a lot of mathematics in this document. Don't worry about it right now, but at least first page tells you what I think is worth noting again. Otherwise, this document is full of mathematics. So we will be doing all that anyway independently. So 2 is not necessary. 3 also, let me just make sure that I'm not missing anything. Again, there's nothing new here. I think other documents have the same thing, but I'll send all these documents anyway. 4, let's say, what does it say? Let's see, what does it say? Yeah, again, intro. I think we are already done with this, but I'll send you all these documents. Please keep them with you. Now, more important for us is what we are going to do in the course. Like it or not, when it comes to analysis of antennas, we will have to use a spherical coordinate system. And that's why I have this document to show you. And I'll be using equations in my notes also, which are same as given in this document. Don't get too scared. It's doable. As you know, we describe the position of a given point in space by using either Cartesian system or rectangular system if you want, or a cylindrical system or a spherical system. Okay. Cylindrical system means z parameter does not change, but x and y are replaced by rho and phi. You have been taught all this several times. I don't want to take too much time on the topic, but this document is worth keeping with you for reference. Conversion from one coordinate system to another requires a lot of formulas which are all given in this document. We will be dealing with a spherical coordinate system, which is described in terms of parameters r, theta, and phi. Theta is known as the elevation angle, which is the angle that the position vector makes with z-axis. This is how r, theta, and phi defined in spherical coordinate system. For reference, we have shown x, y, z axis also. If you take a point of observation P and join it with the origin of the coordinate system, that distance is known as small r. A unit vector in that direction is known as AR or R with a hat on it. Symbols may vary depending on where you look. The angle made by this line, OP line, with z-axis is known as elevation angle. It is denoted by theta. And a unit vector is defined in theta direction also, as shown here. If you take the projection of P on xy plane, that becomes the point below which they have not marked. And that point, if you join with the origin, then that line, whatever angle it makes with x-axis, is known as azimuthal angle phi. That is the third coordinate. So r theta phi can be converted into xyz and vice versa anyway. For a given vector, if you know components in r, theta, and phi direction, you can calculate components in xyz direction and vice versa. There are formulas available. They are given in here. I'll be showing them in my own notes as well. Okay, so there's no need to go through the entire document. You only look for what you need. That's it. It's a very big document on vectors. Vectors 2. Hopefully there is nothing new here. Yeah, I think, yeah, this document probably is unnecessary. Vector 1 is enough, I think, for our purposes. Okay, now let me begin with my own notes. Repetition, I know, but in my own words. One minute. One minute. Yeah, here we go. Can you see the document?
No, sir.
No, you can't. Okay, okay. 1 minute. Yeah, I'm monitoring also. I also cannot see it. Let me do it again. This online education business. Okay, let me come back. Okay, just give me 1 minute. I'll be back. Okay. Can you see it now?
Yes, sir.
Yes, sir.
Okay, good, good. You will be getting all this for sure. Now, the starting sentence is what is already known to you, that we are trying to move from guided waves to radiated waves by using antennas. Okay, so that is written here. The kind of transmission lines that we use are two-wire lines, multi-wire lines, rectangular waveguides, circular waveguides, coaxial lines, strip lines, microstrips, and so on. Now that guided signal has to be converted to unguided or radiated signal using antennas. That's the basic idea. One example besides the EM waves is the sun, which sends us energy through radiation all the time. This is natural example. Okay. Now here is my own description of what happens to the EM wave, starting from the leftmost, where let's say I have connected a source of some EM wave or some signal, which I'm calling Vs. The source impedance is Zs. And let's say I'm connecting that directly to a transmission line, which is slowly opening up. It's one example of a wireless communication system. The transmission line, when it opens, creates radiation. The plane wave, which was traveling inside the transmission line, starts becoming spherical wave. And as you go further and further away, these spheres almost start looking like planes. That so-called plane wave keeps traveling in all directions, depending on the antenna properties. In some directions, it will have more intensity. In some directions, it will have less intensity. In some directions, it may have zero intensity also, almost zero. It all depends on the antenna that you are using. Now, on the receiving side, you will put another antenna in the path of this incoming signal, and you will position it so that you receive as much power as possible. And the received power will be converted, will be slowly brought back to the transmission line by flaring the opening down to the conventional transmission line. And at the output of the transmission line, you should see the signal that you sent with reduced intensity, yes. But waveform in theory should be identical to what you sent. So antennas essentially play the role of the interfaces on both sides. In most practical cases, antennas talk back and forth. The receiving antenna talks to the transmitting antenna also, and transmitting antenna talks to the receiving antenna also. So there may be two-way communication in most practical cases. The receiving antenna also transmits signal at a lower frequency or at lower power for communication purposes with the transmit side. That's the reality, but I'm not showing that in this diagram. Okay. A lot of symbols are being used here, and they will be used again and again in the course. WT will be the power transmitted by the antenna, which will be almost equal to the power being inputted to the antenna, assuming that losses are negligible. WR will be the total power received by the antenna on the right hand side. Okay. The wavefront or constant phase surfaces that we saw in EM theory course are spherical to begin with, but they become almost planes as we go further and further along the direction of propagation. So a lot of it is almost repetition of what I told you. Okay, so let's move to the mathematics now. Basic E and H field descriptions once again for your reference. Symbols will be capital E with a vector sign for electric field, capital H with a vector sign for magnetic field strength, electric flux density with the capital D with a vector sign, and magnetic flux density will be capital B with a vector sign. There are constitutive relationships for a given medium. D is proportional to E, B is proportional to H, through constants which are known as permittivity and permeability. And permittivity divided by permittivity of free space is dielectric constant or relative permittivity. You know all this. For lossy media, epsilon r and mu r will be complex numbers. For lossless cases, they are real numbers, as usual. Values are well known to you. Just for the sake of reference, they are given here again. All this basic EM theory will be needed again in this course. Now, important thing is that you need time varying charges and time varying currents, at least one of them, to produce radiation. And those quantities are given the notation capital J, which is current density in amperes per meter square, and it's a vector, and rho, which is a scalar. Charge has no directions, So rho is charge density in coulombs per meter cube. J is current density in amperes per meter square. These two are supposed to be the sources. If they are time varying, they will produce radiation effect. And radiation effect essentially means calculating E and H, which means D and B. That is the challenge for all antennas. Given a set of J and rho, how to figure out E and H as a function of frequency, as a function of r, theta, and phi, and so on, as a function of the dimensions of the antenna, and so on. Now, a spherical coordinate system, I'm repeating all the formulas once again here. This is how we normally show a spherical coordinate system. You saw that in the previous document also. P is the point of observation. Its projection on XY plane is denoted by Q. And r, theta, phi are defined as shown in this diagram. The unit vectors are also shown. The phi unit vector is supposed to be at 90 degree with r unit vector and theta unit vector. I'm trying to show that in the diagram. Okay. Unfortunately, antennas need spherical coordinate system. These are the symbols that we'll be using. I'll be using r with a hat on it for unit vector along r direction, and similarly for theta and phi direction. Okay, so well-known vector calculus formulas here. Okay. Now conversion, well-known formulas again. X is r sine theta cos phi. Y is r sine theta sine phi. You can easily see it, yourself by looking at the diagram. And Z is r cos theta. So if you know r theta phi, x, y, z can be calculated using these formulas. The reverse is also possible. Now, if an arbitrary vector A is written in spherical coordinate systems, it will have a component AR, a component A theta, and a component A phi. So equation 9 is essentially the way you write any vector in spherical coordinate system. Divergence of A, there's a long formula. There is no need to memorize it. It would be available to you in the exams. Formula for del square in spherical coordinate system is also quite long. Nobody can memorize it, I'm sure. But it has to be available when needed. Gradient, there's a formula for gradient of a vector as well. There is a formula for curl of a vector as well. Curl of a vector is a vector, right? It will have three components, r, theta, and phi. Each component is given by these formulas. Hopefully, there is no mistake in my formulas. These formulas are the backbone of radiation theory. They need to be in front of you for all derivations. Okay. If you know the r, theta, phi components of the curl of A, you can write the curl as equation 15. Okay, so this document is done. Basic. Yeah. Now the next document is, I'm going through vectors carefully because we will have to be conversant with them. Here there are some numerical examples on vector calculus. I think you have done something similar in the past, but for the sake of completeness, it's good to go through these practice exercises. Problem 1 says, convert the Cartesian coordinates given for points below into equivalent spherical coordinates. You are given x, y, z in both cases. Calculate r, theta, phi. Now, the formulas I gave you were actually these, right? Now, you are given x, y, z. So, how would you calculate r, theta, phi? Either you memorize the formulas or take them from literature, or you can do it intuitively also. Since x, y, z are given, let's concentrate on part A first. X is 3, y is -4, z is 1. Okay. First of all, if I divide equation 2 by equation 1, I get tan phi equal to y upon x. That means phi is tan inverse of y upon x. That's very easy to calculate. Second thing is, if I square equation 1 and 2 and sum them up, I'll get x square plus y square equal to r square sine square theta, because cos square phi plus sine square phi will go to 1. And then with that equation along with 3 can be used to calculate r and theta. This is what I have done in this solution. So the formula that essentially come out are theta equal to cos inverse of z by r. R, of course, is equal to square root of x square plus y square plus z square. That you could imagine, I'm sure. And phi is tan inverse y upon x. So conversion is very easy once you know the formulas. And that is what I have done here. Hopefully there is no mistake. For part A, I got r equal to square root of x square plus y square plus z square, which gave me square root of 26. Phi is tan inverse of y upon x. I plugged in the values of y and x. I'm talking part A right now. Okay. Part A had these values. So I got phi equal to minus 53.13 degrees. By the way, tan inverse has more than one solution. So I have taken the second solution also just in case. Theta is tan inverse square root of x square plus y square divided by z square, or cos inverse of z upon r. You can use either one of them to figure out theta. I got 78.69 degrees, and other solutions are possible also, I suppose. I double checked also my calculations by putting these values back in the original formulas, and I think I got x, y, z as they were supposed to be. Okay. Part B is a repetition with different numbers. You can go through it carefully once you get the document. Now, second problem actually is more interesting because this is what we may end up doing in antenna theory. Convert the following equation to the equivalent equation in the spherical coordinate system. X square plus y square equal to 4x plus z minus 2. Solution is simple. Put x equal to this, y equal to this, and z equal to this. Use equation 1, 2, and 3 and substitute in the given equation. The result that I got is given here. The given equation in spherical coordinate system becomes what is shown within the rectangle. Double check the answer once you get the document. Lot of vector identities that may be required or may not be required also. It depends. Let's see. Divergence of curl of any arbitrary vector is 0. We may need it several times. And these identities are independent of the coordinate system. They apply to all coordinate systems. Curl of gradient of any arbitrary vector, arbitrary scalar is 0. I am not proving anything. They are well-known vector identities. Divergence of gradient of a scalar is del square V. Del cross A equal to minus del square A plus del of del dot A. We will be using it several times. Del dot A cross B, there is a formula for that. Del of AB, where A and B are scalars. That can be done also. Del dot of A, B, where B is vector. A lot of formulas are given here. We may not need everything, but I thought it's a good idea to have one page in the notes where these identities are there, just in case we need to refer to them. Direction cosines, you know this. We may not need, let's see how it goes, but for the sake of reference, I have included a discussion on direction cosines of vectors. They are related to the angles that the vector makes with the different axes, x, y, z axis. No need to solve problems on direction cosines itself, but in some antenna discussions, they actually talk about direction cosines. This is why I have included a small refresher on this topic in my notes. Now, formulas. Again, if you are given a vector in XYZ system, that means rectangular system, what are the formulas to convert the vector into a spherical system and other way around? Same vector expressed differently. Equation 19 expresses vector A in Cartesian system. Equation 20 expresses the same vector in a spherical coordinate system. The relations between AX, AY, AZ and AR, A theta, A phi are known and are repeated in this document. Again, I have drawn the diagram for the sake of reference. These are the formulas. Maybe you can derive them, but I generally go by what is given. I don't care about deriving these things. First of all, the formulas given here are for unit vectors, but even for actual components, they will be based on these formulas. Unit vector along r direction can be written in terms of unit vectors along x, y, z directions using equation 21a. Unit vector along theta direction can be written using equation 21b. Unit vector along phi direction can be written as equation 21c. And based on that, this summary table is there, which repeats same formulas in a tabular form. Converse is also possible. You can write formulas for unit vectors in x, y, z directions in terms of unit vectors in r, theta, phi directions. These are the formulas. Now, one problem. The magnetic vector potential A, assume it's a vector. You don't know what it is, but let's say it's a vector that is being produced by an antenna, and you have been told that it has only a z component. That means AX is 0 and AY is 0. This is an application of the formulas that we have done recently in this document. If A has only z component, write the formula for A in the spherical coordinate system based on the formulas that we have just now looked at. Now, I have given you formulas for unit vectors only, but they can easily be translated to similar formulas for components of the vector in a spherical coordinate system versus rectangular system or other way around. These are the formulas. AR is AX sine theta cos phi plus AY sine theta sine phi plus AZ cos theta. A theta is AX cos theta cos phi plus AY cos theta sine phi minus AZ sine theta. These are easily provable. A phi is minus AX sine phi plus AY cos phi. Now, what you are given in this particular case is AX is 0, AY is 0, AZ is 0. AZ is not 0. So, substitute in these formulas. Your job is always to pick the right formulas from the literature to get to the answer. If I put AX is 0, AX equal to 0, AY equal to 0, AR is simply AZ cos theta. Yeah, that's the answer. A theta, after you put AX and AY 0, will become minus AZ sin theta. We actually will be using these formulas when we come to dipole antennas. It is a sort of rehearsal for that right now. And AZ, sorry, A phi is dependent only on AX and AY. So if AX and AY are 0, A phi has to be 0. That's the answer. Given AZ will help you in calculating AR, A theta, A phi by using these three formulas. Essentially, there is no A phi if the vector is only z directed, which is intuitive, you know. If vector is along z direction, it will have no component in the xy plane. As simple as that, right? So that is what you are seeing here. Okay, direction cosines. Maybe you don't want to do it right now, but just in case you are interested, this is the way to calculate direction cosines of a given vector. In fact, there are two vectors given to us. The first thing you do is, in both cases, calculate the magnitude of the vector, which is square root of 3 square plus 4 square plus minus 6 square in one case, and similarly for the second case. Then you take the coefficient of, or let's say you take the x component of A and divide it by the magnitude of A, you get the direction cosine 1. And similarly, you do the second direction cosine by dividing the value of AY by the magnitude of A, and so on. So that's what I'm showing here for both the vectors. Direction cosines can be easily calculated if necessary using this straightforward technique, which I'm sure you are aware of. Now, even more important is what we actually need to do in antenna theory, that if you are given direction cosines of two vectors, how to calculate the angle between the two vectors. There's one way which is depending on the dot product of the two vectors that can be done using equation 25. There's another way which is based on cross product of the two vectors, which can be done using equation 26. Okay. And there is one more way, which I think I missed out. There is one method here. Maybe it got missed out here somewhere. There's, yeah, this is the one I missed out actually. Yeah, this is a very important result for antenna problems. That if you know the direction cosines of two vectors, the angle between the vectors can be calculated by using this formula. If direction cosines are LA, MA, and NA for vector A, and LB, NB, and LB, MB, and NB for vector B, you simply use formula LA, LB plus MA, MB plus NA, NB and take cos inverse of that to get the angle between the vectors. This way you don't have to worry about doing vector product or dot product of the two vectors. An alternate method, which I have verified in my notes for a given problem. Sometimes it is faster to do it this way. Lot of calculations based on vector analysis. But anyway, this is more or less what I wanted to tell you about vectors. Okay. Now the third document, I don't think we'll be able to finish it today, is where the analysis of antennas based on EM theory is introduced, keeping in mind all the vector theories that we have looked at. Well-known Maxwell's equations repeated here for the sake of reference. Those of you who have forgotten, it's a good idea to brush up all this once. We will be using the notation dot on top of a vector or even on top of a scalar to represent partial derivative with respect to time. If there is second order derivative with respect to time, we will be using two dots and so on. And Maxwell's equations applied to e to the power j omega t type of time dependence means derivative with respect to time will be replaced by j omega. Second order derivative with respect to time will be replaced by j omega multiplied by j omega, which is minus omega square, and so on. Remember, here our focus is very different compared to transmission lines. We used these equations for rectangular waveguides, circular waveguides, etc. also, right? But here our focus is to have these equations solved in the presence of two sources, rho and j. If those sources are not changing with time, no radiation will occur, which is what theory would also prove. For radiation to occur, rho and j have to be time varying. At least one of them has to be time varying. And by the way, in reality, rho and j are never independent of each other. One affects the other. That's another side of the story, which I'm not going to talk about right now. Well-known numerical values again for mu naught, epsilon naught, etc. Just in case you don't recall them. Speed of light in space, in free space or air, is almost 3 into 10 to the power 8 meters per second. Now, how do you solve a given radiation problem? That's the conceptual challenge. In theory, I guess you would say, well, what is the problem? You are given rho and j, solve Maxwell's equations and figure out E and H. Yes, sounds good, unless you try it. Until you try it, rather. It's not easy to directly solve Maxwell's equations for a given set of rho and j values. The method that mathematicians adopted was introducing two fictitious quantities called potentials, which are intermediary steps. One of them is known as electric scalar potential V, and the other one is known as magnetic vector potential A. To have these potentials in the game helps in simplifying the mathematics involved, for radiation problems at least. In fact, even for rectangular waveguides, if you recall, I had used the concept of potentials for analyzing the waveguide for TE modes and TM modes. That is generally not done in the books, but I do it that way. There also it helped in simplifying the mathematics. But for radiation problems, it is invariably the case that we don't directly solve Maxwell's equations for E and H. Instead, we first go for figuring out A and V, or at least one of them, and from there we calculate E and H. Now, how do you define A and V? Read this carefully first. In theory, any radiation related problem, rho and J given, find E and H, that is the challenge, can be solved using Maxwell's equations. In practice, the mathematics involved usually become tractable only by using the concept of two hypothetical quantities called electric scalar potential V and magnetic vector potential A. Don't get scared, it is doable. You'll find it very interesting once you start actually using it to real antennas. Note that radiation would occur only when rho and J, at least one of them, is time varying. They don't have to be periodic, by the way. They can be non-periodic also. But we will be dealing mostly with periodic time variations. A is that hypothetical vector whose curl gives us B. That's the way it is defined. There's a reason for it. This definition actually satisfies Maxwell's equation number 4 directly. If you define B equal to del cross A and substitute it in fourth equation, del dot B equal to 0. That means del cross A equal to 0. And if you interchange the position of dot and cross, you get 0 on the left side also. So del dot B equal to 0 is the basis on which A has been defined this way. Because this definition automatically ensures that fourth Maxwell's equation is satisfied identically. Once you define B equal to del cross A, H is obviously 1 upon mu into del cross A. No question about that. Right? I think you must be getting bored. I realize that. Just 5 more minutes, okay? Believe me, this background, once you are over it, will not be needed again and again. There will be formulas coming out from all this theory that we will be able to apply to all practical antennas. But theory is important. So A is defined to be this way because it satisfies Maxwell's equation number 4. Now suppose I take this definition A and put it in equation 1. Del cross E equal to minus dB by dt. Okay. What do I get? Del cross E equal to minus dB by dt. And B is del cross A now by definition. So I get minus d by dt going inside, del cross coming out, I guess minus del cross of dA by dt. Now, both left and right side of this equation have del cross. So I can combine left and right side together to write this, right? Del cross of E plus dA by dt should be 0, based on the definition of A that we have started with. Now we know that this is an identity I have already shown, that del cross of gradient of a scalar, curl of the gradient of a scalar is always 0. So compare equation 10 and 11. There's 0 on the right hand side on both, and there is del cross on the left side on both. That means E plus dA by dt should be del of a scalar, hypothetical scalar. This is why, in fact, a minus sign is introduced for physical regions. What we do is we define E plus dA by dt as minus del V, where V is the second potential involved, called electric scalar potential. Equation 13a is the way V is defined, and equation 8 is the way A is defined. These two potentials, once defined, can help in simplifying, as I said, a lot of analytical challenges. Okay. You can rewrite equation 13a as 13b also. If you use dot symbol on top of A, then this is the way to write. And by the way, if time variation is not there, then dA by dt will go to 0. You will simply get E equal to minus del V, which is well-known formula in electrostatics. Gradient of a potential leads to electric field. So this kind of confirms that we are doing the right thing. Okay. I think I will stop here today. There's enough theory for today. And next time I'll take further based on this formulation and derive some differential equations which will lead to solutions for A and V, which from that point on will become the basis on which we will solve radiation problems. Okay.